Evet, başlayalım. Now I'll talk about separable equations as an application of this integration. But before that, I want to say a few more things about substitution. Okay, so we'll start with separable equations, differential equations, plus some more substitution. Okay, so let me check if this is working. Okay, so this one is very popular. So before that, okay, so integration, another integration. So this pen will not do. Let me take this. So integral of, I'll do, okay, let me continue with what we did last hour. Sine 30x cosine 35x dx. Okay, so in such things, that if one of them is odd, then you associate it with dx. Okay, so that's the trick we play with these equations. Sine 30x cosine 34x times cosine x dx. Okay, so this part you recognize as d sine x. So this part you recognize as cosine square x to the power 17. And cosine square x is 1 minus sine square x to the power 17. Okay, so now everything is in terms of sine x. Okay, so this thing becomes, here you decide to put u equals sine x. Okay, then everything becomes a polynomial in u. This is u to the power 30, and here you have 1 minus u squared to the power 17, and this whole thing is du. Okay, so you see now you can do it. Okay, if you want, you can do that. Okay, so another thing we want to do with sine and cosines is the following thing. Suppose you just have sine square x. X. Okay, so in these cases we use the half angle formula. So this is again a trick that you have to use immediately when you see sine square or cosine square. Okay, so here we use half angle formulas. Okay, so what is sine sine square x is equal to, well, this must come with cosine 2x. Okay, cosine 2x is cosine square minus sine square. Cosine square can also be written as 1 minus sine square. So you simplify from that. So let me see. You should always have plus or minus sign somewhere here. 2x over 2. And cosine square x is 1 plus cosine square x over cosine square cosine 2x. I put the 2 in the wrong place. Okay, so these are the half angle or double angle formulas, whichever way you want to look at it. Are they correct? Nobody is sure. Okay, let's check this one. 1 minus cosine 2 square. Well, I know that that's cosine square plus sine square x over 2. Okay. 1 minus cosine square is sine square. So this is 2 sine square x over 2. 2's cancel, and I get this. So here I'll have the same thing, except that since I have plus here, I have minus here, I'll have 1 minus sine square, which will give me extra cosine square. Divide by 2, I'll get cosine square. Okay, so the formulas are correct. Okay, now instead of sine square x, I write this integral 1 minus cosine 2x over 2 dx. Now this is better than this one because I don't know how to integrate sine square x, but I know how to integrate sine x. Okay, it doesn't matter if I have 5, 2, 7 inside x because differential of the inside is just dx up to a constant. Okay, so this one is now easy. This is integral 1 over 2 dx minus 1 over 2 integral cosine 2x dx. Okay, so this one is x, so 1 over 2x minus antiderivative of cosine is sine. Okay, so here technically you have to do a substitution. You have to let u equals 2x, but we can do it in our mind because it's just a simple no powers. Derivative of sine x would be cosine x, but I need 2x, so you take sine 2x. Derivative of sine 2x will be 2 cosine 2x. I don't have 2 here, so I put a 2 here and divide by 2. 1 over 4 sine 2x plus c. And as I said before, the nice thing about integration is you just check. You take the derivative of this side, simplify, and you get sine square x. Okay? When you take the derivative of this, you will get cosine 2x, okay? And you will have this formula. Okay, so you take the derivative of this, you'll get this one, and that one is equal to sine 2x. Okay, so I think that's all we need to recall, we need to do for some more substitution. Now let's go to what we mean separable equations, and let's solve problems on separable equations. Okay, so a separable differential equation is a differential equation of the form find y if y prime is equal to a function of x times another function of y. Okay, and most of the time we need an initial condition, or we call this boundary condition. Okay, so which is y at some point a is equal to the value b. Okay, so this thing is necessary because you see, suppose I manage to find y. If I add a constant to y, it will still satisfy this condition. Okay, y prime equals this, y prime plus 5. Y plus 5, if I take the derivative, it will be again y prime. 5 will disappear. 5 will disappear after I take the derivative. Okay, well, is this thing working? No, let me stop that. Okay, now I feel much better. Okay. So let me give one other picture here. For example, find y such that y prime is equal to 1. Okay, so this is a straight line with slope 1. So which curve is the answer? All of these lines. Okay, so if I take x, y, then let's use this one. Okay, so everybody thinks about this straight line. Okay, so this is derivative of this is 1, but the derivative of this is also 1. The derivative of this is also 1. Okay, so all of these are solutions. So which solution you want? You say, okay, so here is a point here. Okay, so this is the point, say A. Since this is y equals a, So I want this solution. Well, I picked up a bad one, so let's choose this one. Okay? So we say, here we can say such that y of a is equal to a. Okay, so now I know that this is the answer I am looking for. Okay, if I'm thinking about this line, okay, this is how I would ask this in a differential equation. Or if this differential equation is given like this, among all these infinitely many solutions, only this one is selected out. Okay, even if the differential equation is complicated, the situation, the picture is the same. There is one typical curve which satisfies the differential equation, but if you move this typical curve up and down, it still satisfies the equation because the differential equation is about the slope of that curve at an arbitrary point. Okay, so if you don't change the shape of the curve and if you move it up and down, the slopes always remain the same. So boundary condition says that I want that curve which passes through a particular point. Okay, so that's why we have initial conditions. And this type of an equation, which looks very symmetric, shows up very often. So that's why we consider it separately. And we call it separable equations. Later on in differential equation courses, you'll find more complicated methods of attacking such differential equations. Okay, so for us, y prime, okay, so for us, y prime is dy over dx, just changing notation. Okay, then we have y prime equals f of x g of y is dy over dx equals f of x gy. In one variable case, these dx, dy's behave as if you can multiply them. Okay, without showing anybody, just write this one. Take this to this side, g of y, and this is equal to f of x dx. Okay, so I take this to this side and I take this to this side. Okay, so instead of looking at this equation, I look at this equation, and suddenly it looks familiar. Familiar doesn't mean that I can immediately solve it. At least this is something that I've seen before. I can integrate, so this side I can see as 1 over gy. This is my function of y. I want to integrate it with respect to y. And here I have a function of x. I want to integrate it with respect to x. If I integrate these, here I'll have a function of y equals to a function of x. Okay, but at least I found a way of directly dealing with y instead of dealing with the derivative of y. Okay, so this technique is called separable equations technique. Of course, the functions you get here, this function, 1 over g function and f of x, they may be difficult. We may not be able to explicitly integrate them, but at least we have made some progress. Okay, so let's do some examples. Okay, so one example is this. Dy over dx is equal to x squared over y squared. So I play the same game here. I have y squared dy equals x squared dx. Okay, so this is a simple example as far as integration is concerned, but I'm doing it to demonstrate the technique. Okay, so we integrate both sides. Integrate y squared dy equals integrate x squared dx. At this point, I remind myself that this equation means that both sides will give me functions which differ up to a constant. Okay? Because here I'm saying find the function whose derivative is y squared. So there are millions of these. They are basically the same but differ by an additive constant. Okay? So the same thing here. So now I find these things, 1 over 3y cubed. Since both sides will differ by a constant, it doesn't matter if I write constants on both sides, or just collect them on one side. 1 over 3x cubed plus c. Okay, so this this now translates what I taught about at this stage. Both solutions will differ by a additive constant. So this is how I express this. So it is it is superfluous to put an additive constant here and additive constant here because you are saying the same thing twice. Okay, so in this example we could have here, we didn't have any here you see we can also explicitly find y if we are interested in real values. Okay, so here y cubed is equal to x cubed plus 3 times an arbitrary constant. 3 times an arbitrary constant is an arbitrary constant. Okay, so y is equal to x cubed plus c 1 over 3. Suppose we have a boundary condition. Suppose we have a boundary condition. Okay, so suppose y of 1 is equal to cube root olması için ne yapalım bunu? 8. Okay. Then we put this, we use this to determine C. Okay, so just like in that picture, the curve passes through every point if you move it around. So we want one particular point, and we want the curve that passes through that point. Okay, so we put this in here, we get x equals 1 gives 8 on this side. On this side we have 1 plus c 1 over cube. Fazla yaptı. 8, 64. Fazla oldu değil mi? Let's make this 2. I don't want to work with big numbers. Okay, so now we know that c is 7. Okay, because I take cube, this is 8 equals 1 plus c equals 7. So we need this final statement. Y of x is equal to x cubed plus 7 cube root. Okay, so this is the answer to this question together with this. Okay, so this is the question. Among all curves satisfying this equation, find the one which passes through the point 1, 2. Okay, it is this curve. Okay, so that's the meaning of solving differential equations, and this is how you solve separable equations. Here you see the important step was here. No matter how these things are given, you can come up to this step. Now from this step on, you are on your own. You have to evaluate two different integrals. Okay, so we'll learn lots of techniques for these things. If you are lucky, you'll end up with the function of y being equal to a function of x. Most of the time, you cannot solve that in terms of y. So you just leave it like that, and you attempt. If you need a value of y, you start attempting numerical methods to obtain the value of y at a certain point. Okay, so again, this would not be very difficult. Here, you just put these numbers here. You'll get an equation where the only unknown is c, so you can solve for c, and then you will have this equation with a number here. Now you are interested in if you can solve it in terms of y. If you can solve it for y in terms of x, you are lucky. Okay, then you have a perfect solution. If not, then why do you need y? Because you want to find the value of y at certain values of x. Okay, then you use numerical methods. You put x equals some number, so that gives you an equation in y, and you try to find numerical solutions to that. Okay, let's see some more complicated examples. So eventually, okay, so we are at the beginning. Eventually, I'll do something more serious. Okay, so the second one, let's do dy over dx is equal to 6x squared over 2y plus cosine y, where the boundary condition is pi over 2. Okay, so we'll integrate two simple things. We are at the beginning of this integration chapter. Techniques of integration will come later. So we just familiarize ourselves with these things. So if I do cross multiplication, I'll get 2y plus cosine y dy equals 6x squared dx. Now I want to integrate them. Okay, so let me put, since we are at the beginning, let me write this step by step. Okay, now I can integrate these things easily. This is y squared plus sine y plus a constant. I'll put the constant on the other side. This is 2x cubed. Okay, I take the derivative, I get 6 plus an additive constant. Okay, now put x equals pi over 2 should give y equals, no, x equals 1. X equals 1 should give y equals pi over 2. Okay, so this is now pi over 2 square plus sine pi over 2 is 1 is equal to x equals 1. This is 2 plus c. Okay, so here we know what c is. So c is pi over 2 square minus 1. Okay, so hence we have y squared plus sine y is equal to 2x cubed plus pi squared over 4 minus 1. We couldn't exactly find what y is, okay, but we have this one. So now, if you want to find the value of y at a certain value of x, you need numerical methods, because we don't know how to solve this in terms of y. At least I don't know any technique to solve an equation where the unknown is both in trigonometric function and a polynomial. Let's do another easy example. dy over dx is equal to xy squared, x times y squared xy squared, and we have an initial condition, y of 0 is 1. Okay, so we follow the same steps. Up to here, it is routine. No matter how complicated the equations are, you come up to this stage. Okay, so dy over y squared is equal to x dx. I remind myself that I need to integrate these things. Okay, so after this step, the rest is either hard work or luck or impossible. Okay, so here it looks easy. A function whose derivative respect to y is 1 over y squared is minus 1 over y, right? If I take the derivative of this, I get 1 over y squared. On this side, I have 1 over 2 x squared. Okay, I take the derivative of this, I get this. So you must make a habit of checking these things, because in integration, there is no method to find the answer, but there is a method to know if the answer is correct or not. You take the derivative and check if this. So here, since I'm finding antiderivatives, any other antiderivative will differ by an additive constant. I have this. Now I put the initial condition. So now put y0 equals 1. So this means, okay, you don't have to write this. This is what goes in your mind. X equals 0 and y equals 1 will be substituted here. So you have minus 1 equals c. Okay? So we have minus 1 over y equals 1 over 2 x squared minus 1. So this is x squared minus 2 over 2. So let's make it, we are now just playing to solve this. 2 minus x squared over 2. So this thing being equal to this, I can now write y is equal to 2 over 2 minus x squared. Okay? Now, I can check that if I put x equals 0, I get 1. But if you take the derivative of this, you'll get something complicated. You have to, well, if you want to check this, take the derivative of this with respect to x, then divide the answer by y squared. So divide the answer by this and see if you get x. Okay, so that will be verification that this is the correct answer. Okay, I'll do a few more things, and let me see, this one is a little bit... Okay, so after I do this... okay, so we have some good problems coming, but let us first get our hands used to this game. So this is dy over dx equals 3x squared y squared. If the initial condition, this. Okay, so do you see that this is the point 1 over 2. This gives me a curve, hopefully. Okay, and this gives me infinitely many curves, all parallel to each other. Among all those curves, I want the one which passes through the point 1, 2. So that's the geometric meaning of solving these things. So we play with the same game. Dy over y squared is equal to 3x squared dx. I integrate these. Okay, so let me now put the integral sign immediately here. So this is minus 1 over y equals x cubed plus c. And I put x equals 1, and I get 2, 1 over 2 equals 1 plus c. Okay, so here c is equal to minus 3 over 2. Okay, so we get, let's put this here, minus 1 over y is equal to x cubed minus 3 over 2. So let's play the other game, so because I want to reverse this, this is 2x cubed minus 3 over 2. Now I reverse these and multiply by minus 1. Y is equal to 2 over 3 minus 2x squared. Okay, so you see that when I put x equals 1, I'll have 2 over 2, so at least, well, I didn't get that one. Why didn't I get this 2x cube? Yeah, I have 2 here. I forgot this 2. Okay, so if you put x equals 1, you get 2 over 1. Okay, so this is the solution. Okay. So let's look at this one now. X, y, and y of 2 is equal to 9. So I have dy over square root y is equal to x dx. So I integrate this square root of y, if I integrate this, I'll get 1 over 2. I don't have 1 over 2, so I put this 2. If I now integrate this, I'll get this. Okay. If I integrate this, I'll get x squared, and I have an additive constant. Now I put x equals 2, y equals 9. So this is 2 times 3 equals 1 over 2 times 4 plus c. Okay, 6 minus 2 is 4, so c is 4, right? Okay, so I have 2 square root y is equal to 1 over 2 x squared plus 4. Square root y is equal to 1 over 4 x squared plus 2. Okay, so maybe if I write this like this, it's a matter of taste to this. So y is going to be the square of this, x squared plus 8 square over 16. Okay. Okay, let's do something which looks complicated before we start with something complicated. So this is du dt is equal to 1 plus t to the power 4 divided by ut square plus u to the 4 t square, and I have u of 1 equals minus 1. Okay, so it looks complicated, but we can simplify this part. Du over dt, 1 plus t4. You see, I can take t squared out. I have u plus u4. Okay, was it u? Yes, u to the 4. Okay, so this is of the form 1 plus. Let's also simplify this to make it easier for integration. I'm dividing this by t squared, so this is 1 over t squared plus t squared times 1 over u plus u to the 4. Okay, now it is a nice separable equation. I take it to the other side. I'll have u plus u to the 4 du is equal to 1 over t squared plus t squared dt. Now I integrate both sides. You see, now it's easy. This is 1 over 2 u squared plus 1 over 5 u5. I'll put the additive constant as usual to the other side. This is minus 1 over t plus 1 over 3 t cubed plus c. Now I put t equals minus 1 and t equals plus 1 and u equals minus 1. Okay, so I get u is minus 1, so this is 1 over 2 minus 1 over 5 equals minus 1 plus 1 over 3 plus c. Okay, those who are not sleeping, solve what c is. You are, excuse, you are sleeping, so you don't have to solve this. I said those who are awake. What is c?
29 by 30.
What?
29 by 30.
29 over 30 is c. Okay, so we just put it over here now. Okay, so you see there is no hope of solving this in terms of u unless numerically or using some very complicated techniques. 1 over 5 u5 equals minus 1 over t plus 1 over 3 t cubed plus 29 over 30. Okay, so this is the solution as far as we can push it to this separable initial value differential equation. Okay, so let us do this one. This is a little bit more interesting. Let's see what I will do after this. I'll solve this one and then, okay. I'll solve this one and then I'll solve an integral equation, then we can stop. Okay, so what was the number 6? Let's say 7. Find a function f of t such that f of 3 is equal to 2 and it satisfies the equation t squared plus 1 f prime t plus f of t square plus 1 equals 0. When t is different than 1. At this point, there is no reason to suspect that t should not take every value, but in the solution, you have apparently you divide by t minus 1, so then t shouldn't be 1. Okay, so how do we solve this? We change this to a separable equation. Okay, so here we write y equals f of t and f prime t is dy over dt. Okay. Then we have t squared plus 1 dy over dt plus y squared plus 1 equals 0. Okay. So let's change this. We take this to the other side. So we are trying to write dy dt equals something. So we have minus 1 plus y squared over 1 plus t squared, right? So from here we have dy over 1 plus y squared is equal to minus dt over 1 plus t squared. So next I integrate them. What do I get when I integrate these? Did you see this in high school? Do you remember these things? We didn't do this formally in calculus yet. We'll do this later. So if you haven't seen this, you look at, if you don't know the antiderivative of something and your techniques don't work, the next thing you do is you look up a table. The table says that this is the derivative. 1 over 1 plus t squared is the derivative of arctangent t. Okay, so from a table of integrals, derivative of arctangent t, derivative of this is equal to 1 over 1 plus t squared. Okay, so we'll play with arctangent and its derivative, etc. So this is also a nice way to obtain an approximation for pi. Well, not a very slow method, but anyway, we'll play. Arctangent will be very famous. You'll never forget this. So what we find from this is arctangent y is equal to minus arctangent t plus c. Okay, so the next step, well, in most math problems, you have to be a little poet. There is no method to continue from here. You say, what if I do it this way? Arctangent y plus arctangent t equals c. Okay, so I think at this point we can... Okay, let's continue. So here you see I can take the tangent of both sides. So let us call this alpha. Let us call this beta. Okay, so we have alpha plus beta is equal to a constant. So I have tangent alpha plus beta equals C. Okay, so I'm hoping that if I get tangent of this, I'll get rid of this arctangent and I'll have y. So I'll get an expression in y and t. Okay, so we remember the formula, or we look up the formula, look up the addition formula for tangent. So this says that tangent alpha plus beta is equal to, well, you see this is easy because you look at this as sine alpha plus beta over cosine alpha plus beta. I know the addition formula for sine. I know the addition formula for cosine. You simplify this and you get tangent alpha plus tangent beta divided by 1 minus, I think, well, cosine comes with minus, so this should be tangent alpha, tangent beta. Okay, now I know what tangent alpha is. Tangent alpha is tangent arctangent y, so that's y, and this is t. So this is y plus t over 1 minus yt. Okay, and I know that this is equal to some constant. So this is arctangent c. This is an arbitrary constant. So if you take the tangent, arctangent, square root, or whatever of an arbitrary constant, you get an arbitrary constant. So this is the solution I found, but looks like I can simplify it. Okay, so here I didn't simplify it. I simplified it, but okay. So here now put t equals 3, and y now becomes 2. So this is boundary condition. F of 3 equals 2. Okay, so what do you get? You get 2 plus 3 over 1 minus 2 times 3 equals k. So that's your constant. I found the constant to be minus 1, 6 minus 1, and 5. Yeah, okay, so here k is equal to minus 1. Okay, now solve. Now from y plus t over 1 minus yt equals minus 1, we solve for y. Okay, let me skip a few. So it's easy, you just take this to the other side, etc. So what did you get? We find y equals 1 plus t over 1 minus t. Okay, now we know that t cannot be 1. Okay, so this is our f of t, and t will not be 1. Okay, so that is okay, so that is the solution to this question. Find the function f. So the function f is this one, and now you can check that it satisfies those conditions. Okay, so the last thing I want to talk about is something related to differential equations. These are called integral equations. They are of this form. Integral equations. In a differential equation, you want to find a function, but you know a property of the derivative. Okay, so in an integral equation, you want to find the function, but you only know its property related to some integral. Okay? But both of them are related because at this point now we know that integration and differentiation are inverses of each other. Okay, if you can't think of anything, differentiate. If it doesn't work, integrate. Okay, so in calculus you can never go wrong. So the example we have is find y as a function of x such that it satisfies this equation. Okay? Equation 0 to x 2t square root y of t dt. Okay, so even though y of x is already given, it is related to itself through an integral. So we still don't have an explicit equation for y. Okay, in these cases, okay, this is calculus. We don't have any idea. So what do you do in calculus if you don't have any idea? You take the derivative of both sides. So fortunately, the derivative of the right-hand side will be simple because of the fundamental theorem of calculus. Okay, so take derivatives of both sides with respect to x. Okay, so this part is dy dx to prepare ourselves for separable equation. This side, this is a constant, it goes. The derivative of this is evaluating this at this point times the derivative of this. So in this case, it is 2x square root y. Okay, so this is a nice separable equation. Dy over square root y equals 2x dx. Okay, what's an antiderivative for this? It should be y 2. Okay, if I take the derivative of this, I'll get 1 over 2 cancels and this goes here. An antiderivative for this is x squared plus a constant. Okay, I can now, since this is easy, I can solve for y. Okay, so 2 comes here. So let me, again, just to emphasize that c is an arbitrary constant. This is x squared over 2 plus c. There is no point dividing an arbitrary constant by 2. You don't get anything new. I can take square of both sides. Now this is x squared over 2 plus c squared. Okay, so what is c? I need an initial condition. So where can I find an easy initial condition? Looking at this, for which value of x can you evaluate the value of y? 0, because you see you want to get rid of this integral. So from star, y of 0 is equal to 4. Okay, so this is how you get your initial conditions in integral equations. You just kill the integral by an appropriate choice of the value. If instead of 0, if I had 10 here, integral from 10 to x, I would have y of 10 equals 4. Okay, so we put that here. 4 is equal to c squared. Okay, x equals 0. So c is equal to 16. And finally, y is equal to... Birisi bağırdı. Demek ki herkes uyumuyor. İyi. Okan Hoca'ya söyleyeceğim. In my class, not everybody sleeps. Okay, so c is 2 plus 2 square is the answer. Okay, so this is the question. Find y such that it satisfies this integral equation. The answer is this. Okay, so let's stop here today. On Friday, we'll start with the areas and volumes, and we'll have our surprise quiz.